Hello everyone, I am here with a video to help explain to you guys z-scores and percents on the normal curve. Don't like the way that UC Scout's doing this one, so I gotcha. Let's move on to the first slide. I just want to remind you guys really quickly about what we did prior to our testing week, which was to discuss the empirical rule on the normal curve. On the empirical rule, we've got that 68% of the curve is occurring in between this zone, 1 standard deviation from the mean. 95% of the values on the curve are happening in this zone, 2 standard deviations away from the mean. And in 3 standard deviations from the mean, we're getting 99.7, or I believe UC Scout is simplifying that to 99.5 from 3 standard deviations out from the mean. There's still some nominal amounts that go here, and this is a hypothetical and infinite curve, so you can be 10 standard deviations above the mean. It's just a very, very low value. Notice that we're also including up here 50% to the left and to the right because this is a symmetrical curve, which we can use to our advantage to cut this purple zone into half. 68% is cut up into 34 and 34. For 95%, what we do is we subtract that 68% firstly to get the 27% that's left in the green zone, and then divide that by 2. And then on the remainder on the outside, there is, depending on how you're looking at it, in this case, 4.7% on the outside because we're using 99.7 for this particular diagram. Cut that in half to get 2.35%. Using combinations of the 50 and these values, we can solve some problems that answer quantities. Remember the value 30. Let's look at an example. Scores on a test are approximately normal. A mean of 70 and a standard deviation of 10. That means I can fill this out with 80, 90, and 100. Going to the left, I've got 60, 50, and 40. So there's my normal curve, approximately normal. It tells me that there's 150 students taking the course, and it's asking how many of them failed the test. So we're going to go in here and we're going to look at what failing means, which is going to be less than 60% on the test. So that means that anybody in this zone right there failed the test. Now let's consider what percentage of students that is. So remember, looking back at the previous slide, that we have 68% here, 95% here, and 99.7% here. Okay, well, if 99.7% is here, that gives us 2.35% in just this little segment right here. And then in this little portion right here, let's see, my gosh, why can't 13.5% right here. Sorry, I had to go back and reference that, which is totally fine. I'm going to go ahead and add those values up. I've got 2.35 plus 13.5%, and I'm going to get a total of 15.85% of students failed the test. How many students scored an A? I'm going to go ahead and I'm going to label the same diagram: 80, 90, 100, 60, 50, 40. And in this case, scoring an A is going to be above a 90%. That is just a single section right here, which is that 2.35 section, and we can be pretty direct about that. So we've got 2.35% in this little area, and then we had a total of 15.85% in this red area. Notice that I am drawing a quick little diagram. I had it ready to go on my slide, but you can always sketch one pretty easily. I'm starting with the mean, and I am labeling 3 standard deviations out. I'm marking the value of interest, and I'm shading the area of interest, and that's a really important piece of showing some work when doing these probabilities. We want to talk about z-scores because this is how most people communicate about values on a standard normal curve. Z-scores are a really easy way to talk about how a value compares to the rest of the distribution. A z-score is essentially how many standard deviations above or below the mean a value is. So back on our previous section, an A was 2 standard deviations above the mean. The A was right here compared to the 70. 2 standard deviations below creates a z-score of 2. That's it. This was 70. 60 was failing. This is 60. That's a z-score of 1 standard deviation below. This is a z-score of -1. It's pretty easy. There's a formula associated with this which feels complicated, but oh my goodness, please don't get lost in the complication of this. It's really just dividing up the distribution into portions of standard deviations. Whatever z is going to equal is going to be your value of interest, some x value, minus mu. This Greek letter mu stands for the mean. And divided by sigma. I'll write that down actually. Sigma is standard deviation. The standard deviation is the width of one of these little segments right there. And the mean right there is mu. You will often see values on the normal curve written as mu plus sigma, mu plus 2 sigma, mu plus 3 sigma, because we're literally going up and down in terms of standard deviations. Mu minus 2 sigma, mu minus 3 sigma. So when I talk about my value of interest minus the mean, what you're finding is the difference. And then you're dividing by sigma to just turn that difference in terms of standard deviations. So let's look at some examples so I can make some sense of this formula for you. Here we've got an example. Scores on a test are approximately normal with an average of 75 and a standard deviation of 10. Okay, before I even read on, I'm going to start with my sketch. I have an average of 75 and a standard deviation of 10. There we go. Okay. What is the z-score for a score of 85? So let's look at this. 85, that is 1 standard deviation above, z equals 1. What about a score of 70? A score of 70 is going to be right here, smack in between 65 and 75. That is half a standard deviation below the mean. That is a negative 0.5. Let's see what that looks like when we use the formula. If I use the formula, I've got 70 minus 75 divided by 10. Well, 70 minus 75, that means I'm a score of 5 below the mean. In terms of chunks of 10, that gets me the negative 0.5 we already knew by looking at the picture. It's a difference of -5 counted in chunks of 10. That's why we're dividing. Why do we care about z-scores? Well, for one, it gives us an easier way to talk about where values are in the mean. For two, we're going to be able to use a table to look up some values, which I'm going to show you in a second. But for reason number 3, it's because it helps us compare apples and oranges across different types of distributions. So in example number 2 right here, you're going to see a student in another class had a score of 90 on a test that was approximately normal with a mean of 80 and a standard deviation of 15. Okay, this is a whole new distribution. Poorly drawn. Let me start out. Sorry, you guys didn't even see it because I erased it. Okay, we've got a mean of 80 and a standard deviation of 15. So I'm going to go So I've got 95, 110, 125. Is this even practical? Nope. That's why these are all hypothetical distributions, 50 and 35. Okay, which student did better on their test? The 85 from the first class, which is right here, or the 90 in this class? Well, let's see, where is 90? It's going to be about here. Let's see, a z-score, 90 minus 80 in terms of chunks of 15. That's 10 over 15. This is 2/3, 0.67. Which one of these students has a better z-score? A z equal to 1 or a z equal to 0.67? This student is a full standard deviation above the mean in their class. This student is not quite a full standard deviation above the mean. They might have a better score, but relative to the rest of the class, And the way that this teacher graded, he wasn't in like the top percentages of his class quite as close as this student was. This student scored better than more other students in their class. So which student did better? This guy. This is that standard normal table I was just telling you guys about. Oh my gosh, there's a lot of values on here. Don't worry about them too much. Look on the left. What you're going to see are the first 2 digits, a whole number plus 1 decimal for z-scores. These are negative, and right here are positive. More on why there's both in a minute. And what you see here are the second decimals. And what we're going to do is we're going to combine these values to get a percentage of the curve that exists to the left. Always with these tables, you will have generally a key, or they will explain to you that they are looking for an area to the left of the curve. So this is for that one right there, and then I'm going to do another curve because for the positive values, that means that we're going to have a positive value above z equals 0, which is the mean, which means I'm going to be looking at more than half of the curve, and that's going to be for this positive table. So we'll talk a little bit more about how to use this in a moment, but you do need all of this. Notice that it only goes down to negative 3.4 and up to positive 3.4 because look at how close to 100% or 0% it becomes by the time we get out that far. At exactly a z-score of 0, we have exactly 50% of the curve, and we can see that at 0.0 here and at negative 0.0 because that's just 0. So those are the same value on both of those. Let's take a look at how to use this, and I've just copied snippets, relevant snippets of the table for each problem, but you guys have this entire document posted in Canvas for you to act. Alrighty guys, so let's look at how we can use this table. Here's a problem we've already done. This isn't actually a new test. Mean of 70, standard deviation of 10, 80, 90, 100, 60, 50, 40, and we want to know what percentage of students failed the test. That is all of the students off to the left. We've already done this problem earlier, but I want to show you how to connect this to the table. Let's think about this in terms of z-scores. So my x value here is 60. My z value, 60 minus 70 in terms of 10 is negative, not negative 10, but negative 1. I'm going to look at the table. This would be negative 1.00. I'm going to scroll down here, and I'm going to go all the way down to negative 1.0, and then I'm going to find, well, what third digit do I want to add there? I want to add a 0, so I'm going to find that here, and I'm going to scroll down until these guys meet, and that's my value right there. This equals 0.1587. The values on this table are given to you in terms of area, as fractions of an area of 1. So this corresponds to 15.87% of students. You'll recall that that's pretty much exactly what we got earlier when we were using approximations based on the empirical rule. This is a little bit more precise, but very, very close to what we got earlier. Moving on. Now let's do one where it's not quite so obvious with the z-scores. Adult men's heights in the U.S. are approximately normal with a mean of 69 and a standard deviation of 2.1. As always, let's start out with 69 inches and then 2.1 inches. 71, not 0.1, 0.1, that's 2.1. 73.2, 75.3, going back down, 67, so let's see, that's 66.9, 64.8, 62.7. Okay, what is the probability that a randomly chosen adult man in the U.S. is shorter than 5.2, or not 5.2, 5'2"? Okay, well, 5 feet equals 5 times 12 equals 60 inches. So 5 feet 2 inches equals 62 inches. Okay. Well, where's 62 inches? Oh my goodness, it's so far to the left here that it's like this area way, way, way down here. I could draw a line there to show you that it's to the left of 3 standard deviations below. So my z-score should be less than -3. Let's figure it out though. Z equals 62 minus 69 in terms of chunks of 2.1. This is where you're going to have to bust out a calculator, but I do get -7 divided by 2.1. Sorry, using my calculator really quick, guys. -7 divided by 2.1, and I get negative 3.33. All right, let's go to the table. Negative 3.3. What decimal do you want to add right here? I want to add a 3. So I'm going to go down and over. Here's my value. Here's how we write this. The probability that x is below 62 inches is equal to the probability that z is below negative 3.33, which equals 0.0004 or 0.04%. There's a less than 0.04% chance, or not less than, but equal to roughly, percent chance that a randomly chosen man would be less than 5 foot 2 inches in the US. Okay, another example for you guys. Adult men's heights, again, so we've got the same distribution. 69, 71.1, 73.2, 75.3, going back again. Okay, what is the probability that a randomly chosen adult man is taller than 6 feet? 6 times 12 gets us 72 inches. Let's graph that on here. So we're going to go here to 72 inches is going to be somewhere in there. I'm looking for the area to the right this time. This is going to be a little bit different. So notice that firstly, I'm going to have positive z-scores. So notice that I've given you the positive side of the table. But let's figure out exactly what this z value is. Z equals 72 minus, oops, I don't know what I just wrote. 69 divided by 2.1. Again, bust out my calculator. I get 1.43. It's actually 1.4285, blah, 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 blah. So I'm rounding carefully to 1.43. The probability that x is going to be above 72 inches is equal to the probability that z is going to be above 1.43. Well, let's look something up. The table is going to be 1.43. It's going to be this value right here. That's not the probability above. That's the probability below. That's this area. This area right here is 0.9236. Remember that the whole curve equals 1, so I just need to subtract from 1. So what I'm going to do is I'm going to look up and I'm going to say, oops, I meant to do that in red, 1 minus the probability that z is below 1.43, because that's the number I actually just looked up on the table, 0.9236. 1 subtract that value, and I get 0.0764 or 7.64%. Your final answer should make sense as a percent. The red area that we shaded is small. It is a small percent. If I had stuck with my 92%, that does not make sense that this small portion of the curve right here would be 92%. So double check your answers when you're done. Okay, last slide. Working backwards. Again, 69 with standard deviation of 2.1. How tall is the 75th percentile of men's height? Percentiles means that the values up until there that you would be at 75% of values would be below where you are. Well, we know by the empirical rule that this is going to be 68 right here, that this is 50 here, so somewhere around here, right? We don't know. Let's figure that out. I'm going to put a little question mark there. Oh, I needed to label my graph. 71.1, 73.2, 75.3. Sorry, I need to keep redoing this. Oh, no, 66.9, 64.8. Sorry, guys. 62.7. Okay, well, I don't know. Let's find out. What we want to look for is where do we see 0.75 on the z-table. So we know that we're to the right of the mean. So let's see where the value is the closest to 75%. So here I'm seeing 50%, 60%, 70%. Here I'm getting up to 80%. So let's see. 0.7486, 0.7517. So we have to pick which one we're kind of closer to. This one is 0.0014 away. This one is 0.0017. So this is actually closer. So my value that I'm going to go with is a z-score of, hold on, I just lost it because I went to go get my different pin. Sorry, where did it go? Here it is, right here. So right there, this is a z-score of 0.67. We're going to use our z formula to go backwards. So this was not correct. It's right here, 0.67. All right, let's figure that out. I'm going to go to my formula, x minus mu over my standard deviation. Okay, I don't know x, but I do know my standard deviation this time, so I'm going to plug into the left. X is my variable I don't know. I do know my mean. I do know my standard deviation. I'm going to start solving this equation by getting rid of my fraction by multiplying by 2.1 on both sides. I get 1.407. And then lastly, I'm going to add 69 to both sides, and I'm going to get that x equals 70.407. This is all in terms of inches, so let's kind of figure out what that means. So 70.4 inches tall. Let's go ahead and divide by 12. That this is 5.87 feet. We don't normally talk about it that way. So this is 5 feet, and what is 0.87 of a foot? So 0.87 times 12 gets me 10.4 inches. So this is 5 feet, 10.4 inches tall. A man that tall would be at the 75th percentile of heights, where 75% of men would be below him. Sorry for this video running a little long, but you guys should be ready to go with the homework. Let me know if you guys have any questions. Thank you.